Welcome back. Today we're going to discuss Roman numeral 5 with some applications of electric fields. The first thing is called electric potential difference, and typically because of that term difference it's written as delta V, but you may also see it with just a V because the difference will be implied. The definition for electric potential difference is the ratio of the work needed to move a charge to the strength of that charge. So when we write that in the form of an equation, we would have delta V, or V, equal to the work per charge. And work, if you remember from last semester, is measured in joules, and then charge is a coulomb. A joule per coulomb is where we get the term volt, and it's going to be a capital V for the unit. So this one should be easy to remember because the electric potential difference, the symbol is a V, and the units are going to be a V as well. And then just a side note for you, work can also be given by the change in potential energy. So you might see potential energy instead of work come up in some of our problems. So number 3, whenever we see the electric potential difference between two or more positions as 0, that means that there's no actual difference between them, and we say that these positions are called equipotential. That means they have the same amount of electric potential. And our reference point is arbitrary. It's only the differences that are meaningful, and typically that would refer to the positive end of the battery and a negative end of the battery, and we would look at that difference for the electric potential. So a reminder, if we were to actually find the change in something, we would simply subtract the difference between those two values. And we can also call this term voltage. So electric potential difference is kind of a mouthful, so we will probably shorten that down and refer to it as voltage. Now when we get to our circuits, we'll see something like this picture. So if that's not in your notes, you may want to jot that down. The positive end of the battery is said to have a high energy or a high electric potential, and then the negative end would be a low energy. And it's that difference that's going to push the charges through a circuit and cause a light bulb to light up. You can also measure electric potential difference or voltage with what's called a voltmeter, and you may have seen some of these multimeters set out with the AP classes. We're actually going to do a lab where you'll hook them up in a circuit and we'll measure how much voltage there is in our circuit. Now we have this term called a schematic diagram. That's going to refer to a picture that represents a circuit, and each element of our circuit is going to have a particular symbol. For a voltmeter, it's simply a V with a circle around it. And since electric potential difference is also called voltage, typically our voltage source is going to be a battery, and we also have a schematic diagram symbol for battery as well. If there's one battery, we're going to draw one long line and one short line. The long line represents the positive end of the battery, and the short line represents the negative end. And then perpendicular to those, these lines that come out represent the wires that would attach to the battery. If you were to have more than one battery, you simply alternate the long line and short line with each other. So we have positive, and negative. So for each battery, you've got a long and a short line. You don't have to label the positive and negative for each of those lines. You only need to write the first one and the last one. And so if we have 3 batteries, the first long and short line would be positive and negative for my first battery, and then we would have the same thing for my second battery, and then lastly again for my third battery. Now we are going to be doing some labs in class with what are called castle kits, where you hook up circuits together and you're going to work with these symbols again. So if all of this is new to you and you haven't seen it before, we are going to get lots of practice in class. If you remember from the previous lesson, we discussed electric fields. So we can also talk about that electric potential difference in an electric field, as long as that field is uniform, which means it doesn't change at all. And we could represent that electric potential difference or voltage in terms of the electric field. So we would say E for the electric field, and then we would have a charge being moved, because remember, it was the work needed to move a charge could also be the voltage. So if that work happens, then our charge moves some sort of displacement. So I can make some substitutions and come up with electric field times distance as another way to discuss electric potential or voltage. and then our units still turn out to be volts. I went through the derivation for you, and we're still going to end up with voltage. So I have an example problem so we can work through some of these together. This one has two charged parallel plates, so we're going to have two metal plates and give them a charge. They are separated by 1.5 centimeters, and then there's an electric field between them, and that electric field is 1800 newtons per coulomb. So first we want to identify our variables. The distance is going to be what the centimeters refers to, and we do want to convert that to meters. So I would say my distance is going to be 0.015 meters. And then we're also told this 1800 value, which refers to the electric field. Now, in part A, we're asked to find the electric potential difference between the plates. So far, if you look back in your notes, there were two formulas for electric potential difference. However, we would want to use the one that involves a distance and an electric field. So if you look back in your notes, that's going to be this formula right here. The electric potential difference, or the voltage, would be equal to the electric field times the distance. So I'm simply going to substitute those two numbers in. Go ahead and calculate that out and check your answer. And you should see that you get about 27 volts for that electric potential difference. Now for part B, we are asked to find the work required to move a proton from the negative plate to a positive plate. We aren't given any new numbers, however, we're told that it is a proton, and if you look back in that very first set of notes, we have a data table and we are told the charge of a proton, so that's going to come in handy. So again, for part B, we're asked to calculate the work. I looked up the charge of a proton and it was a positive value. If you wanted to write that in to remind yourself it's a positive charge, it's 1.6 times 10 to the negative 19 coulombs. And since we're looking for work, we don't have a force like when we discussed work last semester. However, we do have a charge, and we found in part A an electric potential difference. So that can lead us to an equation that we talked about earlier, where the electric potential difference was simply the work divided by the charge, and all I have to do is rearrange that one. And so now I can multiply the charge on both sides, and then I would simply plug in the value that I got for that electric potential difference in part A, and then multiply it by the charge of my proton. So go ahead and take a moment and do that and check your answer. So when you make those substitutions and type on your calculator, you should end up with a work of about 4.3 times 10 to the negative 18th joules as your final answer. And a quick reminder for you, there is a study guide at the end of your notes, and those practice problems that are at the end do go in order, so you might want to start working on those now. And that way, if you have any questions, there's plenty of time for us to go over anything that you don't understand before your test. And the last thing we're going to talk about today is called capacitance. The definition for capacitance is the ratio of the charge stored to the electric potential difference. And remember, we can also call electric potential difference the voltage, if that's easier for you to remember. And for our formula, this is one of those rare cases where it's really nice that the definition is simply the formula written out in words. So I know there's going to be a ratio. Capacitance is a capital C, and it's the ratio of the charge, which is a lowercase q, to the electric potential difference, or the voltage. Now, if you've been consistent and you want to write a delta in front of that V, feel free to go ahead and put that in there. Now for our units, charge is measured in a coulomb, electric potential difference or voltage is measured in volts, and this is called a farad. I don't know if any of you guys watched Lost, but there was a character named Faraday that was a scientist, and he was actually named after Michael Faraday, a real scientist that worked in the area of capacitance and electricity. So for this unit called a farad, we are going to abbreviate that with a capital F. And then I have a couple of notes for you. Don't confuse the capital C of capacitance with the C for coulomb. They are both in the same chapter, unfortunately. However, capacitance is going to be a variable and coulomb is going to be a unit. So that's one way you can tell those apart. And then the other thing is just a friendly reminder not to forget about your power of 10 values. When we work with capacitance, we're going to have really small values, so you still need to know the power of 10 values, especially for micro, pico, femto, maybe nano. So take a moment and review those if you're a little bit rusty on those values. And then lastly, we have something actually called a capacitor. This is going to be a device designed to have a specific capacitance. And in your Castle kits, we work with ones that look like this. So you're actually going to hook those up in a circuit and see what they do. And when a capacitor is used in an electrical circuit, it's used to store charge. Now on the inside of a capacitor, it's made up of two conductors, and we will see those as the screws attached to the plates. That's going to be our conductor. And then in between there will be separated by an insulator. And the schematic diagram for a capacitor is going to be two parallel lines. They look really similar to the symbol for a battery. However, the lines are the same length. Now, these two lines represent the two conducting plates, and then there's a space in between, which is our insulator. This line and this line are the wires that would attach to those screws on the top when we hook up our circuit. You can also rotate that symbol 90 degrees and have your conducting plates going up and down as long as they're the same length, and then these two lines out to the side represent the wires that we would hook up. So again, we're going to work with a capacitor in your actual lab so that you can physically see what they do and how they work. That's it for today, and don't forget to start practicing on your study guide questions.